I'm Rohit Kumar Singh, the TA for the course Experimental Physics 2. This is our ninth live session. Today I will discuss some concepts of diffraction and will show some examples uh, on how to solve the problems on diffraction. So let's start.
Bending of light, are you sure? Not dispersion, not dispersion. It's diffraction. So okay. Uh-huh. Okay. Okay. So you're saying, suppose this is an obstacle, okay, and there's the light wave coming like this, okay. So what will it do? Hello. So suppose this is a light beam coming. So yeah, you are right. I mean, it will go over it like this, something like this. Yeah. So yeah, this is basically what diffraction is. Now, instead of obstacle, you can have a small hole also, right? Like this, like a slit. And here also you can observe diffraction. So suppose a light beam is coming like this, okay, and if the slit width is of the same order of this wavelength, then you can observe a pattern on the screen here, kept at a distance, suppose d, right? So one such experiment that we can perform in our lab is called Fraunhofer diffraction. Have you heard of this name, Fraunhofer diffraction? Yeah. So what is the difference? What is the difference between these two? Mhm. Yeah, slit. Uh-huh. Are you sure? Is it the distance between the slit and a screen or source and the slit? Yeah, yeah. So in Fraunhofer, you the source is far away, so that the beam of light which is coming should be parallel, right? Yeah. So parallel beam. So now, I mean, so that means the source should be at an infinite uh, distance from the slit, right? But uh, in general, we cannot do that. We cannot always have a source at infinity. So now, what can you do to make the beams parallel? Yeah, exactly. So you can use a convex lens to focus the, yes, diverging beams into a parallel beam. Okay, and when these beams will encounter the slit which has a width, suppose d, then you will observe, so a screen is kept at a distance, say d, capital D, okay. So you will observe a pattern here, and the pattern uh, that you will observe, which it will be roughly like this. So I'll draw the intensity pattern. So it will be like this at the center. Then it will fall like this. Okay. So this is the famous diffraction pattern. Now you have studied interference, right? You know about interference. There, all the maxima, all the fringes are of the same intensity, right? But here the central fringe is has the central fringe has more intensity, and then the intensity goes down. Okay, so this is the typical picture of diffraction. Now, there is, I mean, physically there is not that much difference between a interference and diffraction. Okay, uh, it's just the result that we call. I mean, from a single slit, the result we call it a diffraction pattern. From a double slit, we call it a interference. Now, suppose you have a 3, 4 n slits, then what will you call it? Is it interference or is it a diffraction? Yeah, but what is the phenomena? Is it interference or is it diffraction? Yeah, so we call it, normally we call it diffraction ratings, right? Yeah. So these things are there. And so I'm not going to derive all the formula of maxima, minima positions or maxima and minima. You might have already seen that in lectures, in the NPTEL lectures. Or so what? I'll just write out some of the important formula which we will need. Okay. So one formula is for, so these intensities, they vary like this. Okay, the intensity of intensity distribution, basically this vary as I naught sine square beta by beta. So I naught represents the intensity at theta is equal to 0. Okay, I naught is intensity at this center middle point. Okay, and yeah, and the beta, yeah. So and the beta is given by uh, pi d sine theta by lambda. Okay, and so this comes through the derivation. If you derive, uh, you what you consider is that you make two, two divisions of this slit, and you basically you do the same calculation as you do in the interference, and you get these expressions. Okay, so these derivations are pretty standard. So now for the position of maxima and minima, uh, what you can do is, uh, you can put that, I mean, this intensity equal to 0. Then what will happen is that when it will be 0, when beta is integer times pi, right? And because then the sign is 0, so this will give you the position of uh, minima, right? And so then you can calculate, you can then put at the place of beta your, so d sine theta, and lambda will be so pi will cancel from both sides, and you will get m lambda, where m is plus minus 1 plus minus 2 integer values. Okay, this is for minima. Fine. And then the maxima, uh, so the first maximum, so the you can briefly see that the first minima will occur at, suppose, plus minus, so both side of this center there will be a first minima, like here and here, right? And it will be at lambda by d. Okay, second minima similarly will be at 2 lambda by d, and so on. Okay, now now this one thing you notice here is that the sine theta cannot exceed unity, right? So then the maximum value of m is the integer which is less than b by lambda, right? M will be less than d by lambda, right? Because if it is not satisfied, then the sine theta will go beyond the value of 1, which is not allowed. So it is just a simple note, simple thing to note. Now also, no, this is for the minima, right? Then for maxima, so what will you do for to calculate the maxima? So at in I equal to 0, you have minima. You calculated that very straightforwardly, right? But for minima, what can you do? Uh, do you have some idea? Rajesh? Yeah, so for minima, what we did, that we had the expression for intensity, right? For the, why do you do that? Why do you do that? Maxima, for maxima, why? So what does this mean? Di by d beta. What does this mean? Putting this to 0. Yes, slope. I mean, mathematically it's slope. Physically, what does it mean? So this intensity, so this plot like this. So you see where there is maxima, the slope is 0, right? I mean the rate of change of intensity is 0. So that's why uh, we have this condition, and using this condition you will obtain a result. So when you do this differentiation, you will get sine beta beta minus tan beta equal to 0. So the condition will be beta equal to m pi. uh, this will okay, so sine beta, this corresponded to minima, and the condition for maxima, uh, because one condition will give you minima also, right, from here, because this minima also has the slope 0, right? So, and the other condition which is here, which is beta equal to tan beta, this will give you the maxima condition, right? Yeah, so this is it. Now so one can ask, what will be the uh, distance between two minima or two maxima? How can you calculate it? Yeah, two minima. Yeah, that is the distance of the center. Yeah, 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 yeah. So you have this theta, right? This angular, you have this angle. Then the angular distance will be just 2 theta, right? And what is theta? Lambda by d. Yeah, yeah. But what is theta in terms of which d? Capital D or small d? You're saying lambda by d. You sure? Hmm. D sin theta is equal to hmm, by, yeah. So for the uh, so for first minima, the m equal to 1. Yeah. So theta equal to, yes, you're right. Yeah. So simply the distance between the two minima will be just 2 lambda by d, right? Yes. So this is all you need for today. Okay. And so let's start with some problem. So this is just a child's play. So here it is asked which this following pattern is observed for which experiment. So like we discussed just right now, obviously. Yeah. So there are other options. So do you know how the Newton rings pattern look like? How? Yeah, yeah, yeah. Like this, right? Yeah, and their radius, how they, no, but no, their width. Mhm. Yeah, you're right. Mhm. No, but I'm asking what happens to the width of these rings as the radius increases. They become smaller, right? Yeah. So this is Newton's ring. Then double slit for Fraunhofer diffraction. How does that look like? Mm. So at the center you have a maxima. Then then again maxima. I mean the maxima will all have the same intensity, right? Then single slit Fraunhofer you've seen. Then what happened with the grating? Yeah. So diffraction will be like this, right? Then how can you how do you see interference pattern here? So this will be a overall profile, but the actual intensity will vary like this. So you will have this, right? This. This will be the grating. Okay. So nice. Okay. Then the second problem here. Uh, the question is the screen is placed 2 meters away from the slit uh, in a single slit diffraction experiment. What will be the slit width if the distance between the two minima is 5 mm? Wavelength of the light is given. Okay, we also discussed this just now. So yeah. Mhm. Wait, what are you saying? Two. Mhm. Slit width is not beta. Beta is, yeah, fringe width is yeah, beta. Yes. Hmm. Okay. Yeah. So you can the lambda, and the screen distance, so you can calculate the d, right? Straightforward. Yeah. So it is, sorry, fine. No, no. uh, 10 yeah, yeah, no, 2 lambda d by d is 10, right? Wait. Oh, okay. First 2 minima is given. That is 2 beta is 5. Yeah, yeah, sorry. Then d is just 2 lambda d by 5. And you will put everything 4000 angstrom is 10 to the power minus 10 meters and 2 meters, and then we divide by 5. 5 is mm, so 10 to the power minus 3. So now it will be 4 and 4 will be 16, and 16 into 10 to the power minus 7, which is minus 4, because 10 to the power minus 3 will cancel, then 5 is there. So we have 0 3.2 into 10 to the power minus 4, so 0.32 mm. Yes, correct. Yeah, yeah. Okay. So yeah, this was also a simple problem. uh, Now here another question. So how solar diffraction pattern change when white light is used instead of monochromatic light? So it is a just a statement problem. So what do you think will happen? Hmm. Okay, why that so? Hmm. Okay, yeah, sure. And what about the other distances? What about the why? Yeah, phase difference, and the phase difference depends on the wavelength of the light, right? So white light is consist of many wavelengths. So for each of those wavelengths, uh, the phase difference will be different at, suppose, this position P here, or the white. I mean, because the white light has many uh, colored light, so what will happen is that they will all have some different phase difference for this point, and so uh, you will not observe a single minima or maxima here. You will observe different color of maxima minima, and they will all overlap and give you a colored pattern, right? So yeah. So but do you think the white light, but isn't that a problem with white lights, that it might not be coherent, because you need coherence for, yeah, hello, I'm saying you need a coherent light source, right, to produce diffraction pattern, but we know that the white light is not coherent. Are you sure? No, but when you do the calculation, you do the calculation like in this way, like you do in the interference case, because you consider the slit in two parts, and then you take uh, I mean you take the, like, from this part and this part, and you interfere the uh, wave fronts, right? So you need a coherent source, otherwise won't be. So just give me a think about this. Just give me a minute. I'm coming back. अमेजोन अमेजोन वाला कुछ लेके आया है. हेलो 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 हेलो. Where are you? Rohit. Okay, okay, coming. See, क्या है? Hello. Hello, Rajesh. Are you there? Okay. So, did you think about it? Actually, you need coherent source, but so I mean the source. So you have these incandescent light bulbs, right? So light coming from them is not really coherent, but what you can do is you can make a special kind of white light source, okay, in which, so you will have, suppose, so to make a white light you need 7 colors basically, right? Wavegear, and so I mean these kind of sources are available. I mean you can make this kind of source of light, which will be coherent, instead of containing many wavelengths of light. But you cannot do the diffraction experiment with ordinary source of light, like a light bulb that you can buy in any shop. Okay, so you really need a coherent source. Okay, yeah. So now, fourth problem. Here, a parallel light of wavelength 600 nanometer falls normally on a single slit. The angular width of the central maximum is 60 degree. Find the width of the slit. Again, easy problem, right? So angular width means this. So this is the screen. This is 30 degree and this is 30 degree, and you have the intensity, center intensity, like this. Okay, so first minima, as we see, sine d sine theta equal to lambda. This is the condition, right? So t is simply just lambda by sine, and here theta will be what, 30 or 60? Yeah, this one is theta, right? Not the whole thing. And this this is, so lambda is given. Yeah, 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 just so lambda is given 600 nanometer. So and sine theta is 2 1 by 2, so 2 will be multiplied above, and 10 to the power nanometer is 10 to the power minus 9. Mhm. So what will you get? 1200, 12 into 10 to the power minus 7, sorry, minus 7. This will the meter, yeah, second. Okay, fine. Now, fifth problem. So, what will be the linear width of the central maxima on a screen that is kept 2 meters away from the slit if a light of wavelength 600 nanometer strikes a slit of 0.2 minimum uh, millimeter width? Okay, so as we know, slit width uh, is given as 2 lambda d by d, right? So, and you know everything. Everything is given. Lambda is given, small d is given, capital D is given. So this problem is nothing much. Just put everything and calculate. 2 into 2 meter into 600 nanometer divided by 0.2 minus 3. So 1 2 will cancel, then you have 12 into minus 6 will be here, and so yeah, 2 10 to the minus 2 will cancel from this 100, so this will be 10 to the minus 3, so 12 mm. Yeah, 12 millimeter will be the option here. So these problems actually they are kept here so to just so that what you can calculate if you have. So suppose now here you what what also you can do is, suppose you are using a source of light. Okay, you don't know the wavelength of the source of light, but you can do this experiment. You can observe the uh, width of the central maximum, right? You can measure this. You can measure the distance between the slit and the screen, and you know the distance of the you know the slit width. So from this simple formula you can calculate the wavelength of any light that you are using, right? So that's in this way these you should think about these problems. So okay, let's move to the next problem. So here again same type of problem. Here we have to determine the angular width of the central maxima, and wavelength is given 450 nanometer, and slit width is given 0.02 millimeter. So like we discussed, what is theta? Yeah, lambda by d. But it is not the angular width of the central maxima. The angular width will be 2 theta, right? Yeah. So, and and the is lambda and d is given simply. So 400 nanometer will be uh, 0.02, correct? Because I mean in meters it will be like this, and then 490 and 45, so 0.045 radian, right? C. Oh yeah, this was so simple problem. Then seventh problem, a beam of light of wavelength 4200 angstrom. So do you know what color of light has this wavelength? 420 nanometer. Blue or yeah, should be blue. Yeah. Blue or indigo. This kind. From a distant source falls on a single slit. Uh, the slit width is given. Okay, and the resulting diffraction pattern is observed on a screen 1.5 meter away. The distance between the first dark ring on either side of the central bright. Again, the question is asking you the yeah, exactly. 2 beta. Yeah, 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 exactly. So, I mean, this is nothing but the width of the central maximum, right? Which is 2 lambda d by d. And you know everything. So, 4 to 10 to the power minus 10 and 1.5 meter, and then 1.5 mm. This is there. So 1.5 1.5 will cancel. So and then we will do 42 into 284, and it will be in mm. So 0.84. Yeah. Okay, this one is also simple. Now we have a parallel beam of light of wavelength 45. Again, the this is nearly the same wavelength as the previous one. Uh, gets diffracted by a slit width of 0.3 mm. The angular position of the first minima of diffracted light. So angular position of the first minima is just lambda by d, right? Okay. Very simple problem. So 4500 divided by 0.3. So here you have 10 to the minus 10. Yeah, 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 exactly. Okay, nice. Then ninth problem. This is our second last problem. So here a single slit from our diffraction pattern is formed with white light. For what wavelength of light the third secondary maximum in the diffraction pattern coincide with the second secondary minimum in pattern for red light of wavelength 6300 angstrom. Okay, so this one is a little bit involved. This problem is not that straightforward. So how do you think we can calculate this wavelength? Uh-huh. Okay. Odd multiple of lambda by 2, yeah, like m plus half, yeah, m plus half lambda by 2, right? Oh, sorry, not lambda by 2, lambda. Yeah, yeah, yes. Uh-huh. Exactly. Mhm. I'm not able to, let me write it again. Yeah, so the angular position of maxima is given like this into lambda, okay? And so here it's asking for the wavelength, for what wavelength of light third secondary maximum. So third secondary maximum means this thing. We put m equal to 3, so 3 plus half lambda, and I mean this is theta 3, and for uh, second secondary maximum we'll put 2, correct? Okay, so now the question is they are coinciding, so that means theta 2 equal to theta 3, right? So 3 plus half is just 7 by 2 lambda equal to 5 by 2 lambda, right? This is lambda 3, this is lambda 2. So, and this lambda 2 is given 6300, right? So lambda 3 is just 5 by 7, lambda 2, which is 5 by 7 into 6300. So, and 7, this will be 900, and 4500 angstrom. Yeah. Okay. Then this is the 10th problem. So here you see that that question that we had, uh, where we use the white light, what will happen? So here you see, if we use two different wavelengths, their secondary maximum and uh, third secondary and second secondary maximum are coinciding. So in that way, if you have many colored lights, then other maximum will coincide at a point, right? So that's why you get a colored pattern. So this way also you can see. Now 10th problem. This is the last problem. So here, by observing the diffraction pattern, the two images are said to be just resolved. If so, you know the diffraction pattern is very important while using some optical instruments. Uh, so suppose you are using an optical microscope and you are using it to look at some like bacterias or something. Okay, so there is a parameter called angle of resolution or resolution power of microscope, or telescopes also has resolution power. So those are based on this diffraction pattern, right? And because at the aperture of any microscope or telescope, you will have some diffraction of light, and so uh, that uh, does not permit you to get a what you say, like infinite resolution. You will There will be some finite resolution of any optical instrument. So when do you say that the images are resolved? By observing the diffraction pattern of two sources. Okay, what is the Rayleigh condition? Mhm. So suppose this is the diffraction pattern of first image. Okay, so you're saying if what you're saying, okay, first minima of the second, that means like this, right? Then you say that these two images are perfectly so just resolved. That means you can separate, you can tell that these two images apart. Otherwise, if it is not, if it is something like this, it looks like a single image. So yeah, this is the condition for resolution. Okay, so yeah, that was the last problem that I have to do. Uh, so the problems were really simple. And, so, Mr. Rajesh, can you tell me about yourself? So, what are you doing and why you took this course? Mhm. Oh, nice. Oh, okay, nice. I'm living in Pampa. Yeah. Uh-huh. Okay. Uh, Oh, nice. So, Ramaprabhu. Oh, you were in physics department. Nice. Nice. Aha. Okay, 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 nice. So then you completed your PhD later? Oh, nice. Okay, so you are teaching currently there? Oh, you're teaching. Okay, great, great. So okay, okay, nice. So why did you took this course actually? I'm curious to know. Okay, okay. Yeah. Okay. But this course is very should be very elementary to you, right? Uh-huh. Yeah, that happens. Mhm. Yeah. So yeah, no, it's great that you are still trying to learn. Yeah, yeah, yeah. No, no. Like it's my pleasure. So, so did do you do you attend these lectures regularly, like from the NPTL? Oh, okay. Yeah, yeah. Mhm. Okay. Okay. It's nice. Mhm. Oh. Yeah, 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 yeah. I have some idea. Uh, mhm. Yeah, that's sad. But yeah, you should try to make your lectures interesting so that students might get into some of not all of them will get interested, but at least if you can make two or three of them interested in physics, and if they like get inspired to do something in physics, then that's so I'm from physics department. So, yeah. So my guide is so you might not know him. He joined in 2016, Prabhat Pujari. So I'm working in high energy physics. Uh, so we have a collaboration at CERN, and our field of research is very new in IIT Madras. In your time, James Libby might have joined, or Prafulla Behra. Yeah, so my guide, yeah, Ramaprabhu taught us this FEP course when I joined the PhD. Yeah, 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 yeah. So yeah, he's a good teacher. It's very nice to talk to you. Okay. Uh, yeah, I mean 30. Yeah, my research work is going fine. Uh, just now, I completed one analysis. We are going to paper approval. I'm from Jharkhand. My master's is from IIT Kharagpur. Yeah. Where? No, no, no. Amal Kumar Das. Amal Kumar Das. No, no. He is not. He was not my MSc guy. But yeah, I know him because uh, we interacted. How? What? What? Yeah, yeah. So actually, I get this PMRF. Yeah, yeah, yeah. I get this PMRF fellowship, and for that we have to do an external teaching duty. Okay, we have to interact with the students. Uh, so that's how we have to choose some. You can either go to a college and teach in a nearby college, okay, or you can do this NPTEL session. So, so because I have to, like I had to go to different places, like to attend conferences and so on. So I could not do this like this college thing, nearby college thing. So I chose this NPTEL. Okay, then if you want to ask anything else, otherwise maybe you can join again next week. We'll discuss more. Yeah, yeah, same time next week. Yeah, same on Saturday. Okay, okay. It was very nice to talk to you, Rajesh. All the best. Yeah, yeah. And please do visit IIT Madras sometime. Okay. Uh-huh. Okay. Oh, okay. Uh-huh. Oh, nice. No, it is very good that you are still learning. It's very good. It's very uncommon. Yeah, I really appreciate it. And yeah, and do visit IIT Madras sometimes. It's a college. Yeah, yeah, yeah. Wait, I'll write it in the chat box. So it is my roll number. You know the rule. In your time, what was the rule? This roll number thing was there. Roll number with Ismail. Yeah, yeah, yeah. No, no, no. I'm asking the email ID. Does that work like this? The roll number and then smail.itm.is. Okay. uh, now they have changed it to like this roll number then. So yeah, this is my roll number. I check, send it to chat box. Okay, and yeah, feel free to contact me anytime. Okay, okay then see you then.